Hi, my name is Keegan, and today I will be telling you all about the wonders of torsional resonance mode for atomic force microscopy. Atomic force microscopy, shortened to AFM, is a very high-resolution type of scanning probe microscopy with demonstrated resolution of up to less than 1 nanometer. Here we can see the typical configuration of an AFM. First, we have the probe, which consists of a cantilever, a probe tip, cantilever support, and a piezoelectric element or oscillator. Next, we have the sample and sample holder, which consists of an XYZ drive, stage, and of course the sample. Lastly, and most importantly, we have the laser and detector, which is primarily how AFM receives feedback and data. An AFM generates images by scanning a small cantilever over the surface of a sample. The sharp tip on the end of the cantilever interacts with the surface topography at the atomic scale. This deflects the cantilever and changes the amount and position of the laser light reflected onto the detector. The height of the cantilever is then adjusted to restore the response signal using a feedback loop, leading to topography and atomic force mapping. One of the most important and commonly used imaging modes is tapping mode. Tapping mode AFM is a Brooker patented technique that maps topography by lightly tapping the surface of the sample with an oscillating probe tip. The cantilever's oscillation amplitude changes with the surface topography, and the vertical position of the cantilever is adjusted accordingly. The development of tapping mode enabled researchers to image samples too fragile to withstand the lateral forces of contact mode, where the tip is dragged across the sample. Additionally, much higher scan speeds can be used than in non-contact mode. Tapping mode and non-contact imaging modes were developed in part to eliminate frictional forces between the AFM tip and the sample. This allows fragile samples to be tested and minimizes damage to the tip and the sample, but the tip will be minimally sensitive to lateral forces. Torsional resonance imaging recovers the ability to achieve low-force imaging and the ability to map in-plane forces, not just vertical forces. This also grants researchers the ability to map in-plane, long-range forces, such as electrostatic or magnetic forces. Traditional AFM measurements are sensitive to these long-range forces and force gradient in the vertical direction only. In the torsional resonance mode, the cantilever arm deflects around the lengthwise axis instead of around the width axis. To excite the cantilever into its first torsional resonance mode, drive signals of opposite phase are applied to two piezos. Due to the increased inertia of the tip around the axis of rotation, an oscillating torque is generated in the cantilever. This mode, called TR mode, was first commercialized in 2003 by Brooker. Dan and I were just 4 years old at this time. Lateral forces that act on the tip can cause a change in the torsional resonant frequency, amplitude, and/or phase of the cantilever. Images of topographic structure, mechanical properties, and in-plane force or force gradient fields can be constructed from this data. TR mode has many advantages over tapping mode and other imaging modes. Firstly, one of the main characteristics of TR mode is its ability to maintain probe tip in the near field area at the boundary between direct contact and the long-range force area. Additionally, torsional resonance data yields approximately 20 times stronger contrast than tapping mode at step edges, revealing detailed structures that cannot be resolved in tapping mode imaging. Under the torsional resonance umbrella, there are two additional modes of use: contact mode and weakly coupled interaction region mode, or hover mode. The contact mode for torsional resonance is very interesting. The topography can be measured like regular AFM contact mode, but the contact torsional resonance can also be measured. This leads to lateral contact stiffness, friction, and the derivation of stick versus slip transitions under load. In tapping mode, the tip apex experiences several regions of interaction, from contact to interaction-free state in each cycle. On the contrary, the torsional resonant tip only moves slightly at a near constant tip sample distance z. While there are many applications for TR mode, one of the best-known uses is high-resolution imaging. TR mode uses near-field interaction to control feedback, making the imaging control particularly sensitive to variation of adhesive forces at the nanometer scale. Secondly, The switching between flexural and torsional resonance can be performed as often as desired, and commercial systems allow a user to switch between tapping mode and TR mode on alternating scan lines, allowing near simultaneous imaging of the same sample in both imaging modes. This allows a fast scan, which is sensitive to both vertical and lateral forces, has high contrast at step edges, all without using contact mode. And lastly, TR mode can be used with tunneling AFM to create torsional resonance tunneling AFM, or TR tuna. Quoted from the Brucker website, torsional resonance tuna is an enhanced option that allows tuna to be used on fragile samples by operating torsional resonance mode in place of contact mode. This modification greatly reduces vertical and lateral tip forces on samples while keeping the tip in the near field where tuna currents can be measured, a capability especially important for polymer, thin film, and nanoelectronics applications. As you can see, while torsional resonance AFM is not the most used or important mode, it has its specific uses and opens up many new doors for materials research.